So today we'll be talking about pathfinding and steering behavior. And of course, pathfinding is a very, very important part of most games. I'm going to have some examples here of why that is. I'm going to give some high-level descriptions of pathfinding algorithms. If you have taken 3200 with me, you're probably sick and tired of pathfinding. You never want to see it again, and I completely understand. I will mention what the A-star algorithm is, because it wouldn't really be a game course unless you at least said the name of the A-star pathfinding algorithm. But we will not be doing that sort of thing in this class. When I taught 4303, which is the AI and games class, we go more into pathfinding stuff. But I didn't want to have like, okay, we have 3200, which is AI, then 4300, which is games, and then 4303, which is AI and games. And so you can't have like all three classes just share a bunch of the same stuff, right? And so, but I'm not teaching 4303 next term, so we'll see how Jay Henderson is teaching it, and he has some. He's going to teach it a little bit differently. I'm not sure if he's going to use a game engine or not, but it'll be a great course. It's just that I'm not sure what's going to be in that. I used to be able to say, hey, if you want to drill down into pathfinding, take 4303, but I'm not sure if that's the case anymore. So movement in games. In my opinion, it is arguably the most important part of a large number of video games, because usually the trope in video games is that there's some character that you control in that game and you're moving them around, right? And so who here has played a game where like it looked good graphically and maybe the weapons are really cool, but it just feels, there's something about it when you move around that's just not right, you know? And so and not only does it feel not right, but like it makes the rest of the game not feel good. And I felt this way about a number of games for the old NES. And it was really interesting because people were still like figuring out video games. And now we have pretty standard, no matter what platformer you're playing, you're pretty much going to get the same responsiveness, the same sort of controls. Okay, hold this button to run, press this button to jump. Maybe there's a dash or a double jump or something. But like that wasn't always the case. And there was a time where people were just like figuring this stuff out. And games like, I think like City Connection for the NES, it's like a really interesting game where you're a car as a 2D platformer. So it's a 2D platformer where you are a car, and basically the only controls are turn left, turn right, and jump, because whatever direction you're facing, you're just going in that direction. And there's a bunch of tiles, and the object of the game is literally just to touch every tile in the level. But like when you turn, there's this big animation, and you slow down, and it's just like, I really want to like the game, because it's so simple and it's interesting, but the movement it's horrendous, right? And so I watch a lot of speedrunning of old games, and the speedrunners of that game are just like, they just hate themselves when they're playing this game. But it's like, it's so competitive because it's such a short game. But anyway, that's kind of an aside. But movement is really important, right? If you make the movement fluid and fun and responsive, then the game will be much more fun and responsive. It allows the exploration of the game world and the interaction with the entities in it, right? So it basically enables everything to happen. Imagine like Minecraft if you couldn't move, right? Pretty bad game. Not only does the player move in the game, so you've got to implement the game and mechanics and controls well for the player, but the NPCs and the entities in the game move as well. And so because you're the game programmer, now there might be an AI programmer at the company who handles this sort of thing, but you've got to deal with this. And good movement makes a good game, in my opinion. So the main problems when we talk about movement in video games, at least for AI and NPCs, there's 4 different problems. One is pathfinding. So how will the NPC get from point A to point B? The next one is path following. So if you did 3200, we did pathfinding, but we did not do path following, right? Okay, now I have the path. How do I actually guide the NPC along that path and make them move? There's physics. So, you know, are you in a car? Is there ice? Are you banging into stuff? There's lots of interesting problems when it comes to physics and movement. And also, it may not be obvious, but animation plays really heavily into movement as well, right? Like how if you're running and you turn around, like how does that animate, right? Do you all of a sudden just instantaneously get turned in the other direction, like an old NES game or something like that? Or is there this like more Dark Soulsy, okay, if I'm running this way, now my character puts their foot out to stop the movement and turns around. So movement really makes things, movement makes things possible, but animations make the movement look good. So in this class, we're going to be talking about pathfinding a little bit, and also path following. I'm not going to be talking about the physics or the animation. And so in this lecture, we're going to be dealing with decision making for movement. So pathfinding and path following, but not the other two things. And I do have a couple of videos here. This video sometimes is a bit loud, so I'm going to turn it down. There's just a bit of music in the background. Hopefully. Oh, I gotta turn off the laser pointer to play this. So this is from Saints Row. And the pathfinding in Saints Row is like pretty good, except for when the drawbridge is up. And then this starts happening, right? So this is something that either the developers didn't think about or thought about a lot, right? And I'm not sure which, because Saints Row is kind of like a parody Grand Theft Auto game where everything is just cranked up to like 1,000,000. And so it's very possible that they just saw that and left that in because it was hilarious, whereas some other games might see that and say, oh, that makes us look kind of foolish. This is another type of pathfinding. So I'm about to show this from Skyrim, and it's sort of like a threat-aware pathfinding. So if any of you have played a Bethesda game, you probably know, like, don't die. Like, you're laughing a lot. But here we go. Yeah. So here's an example where we've got the player. The player is moving through this dungeon, and it's a bit dark, so it's hard to see. But you'll hear in the background, hopefully, like, oh, who's that? Right? And the NPC come out to see who it is, but there may be something in the way of the NPC.
Is someone there?
So that was the NPC. Oh, this is super dark. Hopefully you can see it. Oh, here's the next one. So, like, you know, the residents of this dungeon should probably know, like, where the traps are. But this is a Bethesda game, so I'm not sure if that was intentional, right? Because Bethesda games are kind of known for their hilariously bad AI in some cases. And just as another aside, it has nothing to do with movement, but one of my favorite things in the AI of any video game is the fact that aggro in Skyrim and Oblivion was caused by line of sight between the eyeballs of the NPC and the body of a player. And so if you took a bucket and put it over the head of a shopkeeper, the line of sight was broken, and you could steal everything in the shop. So just amazing, right? Like, probably, that's the sort of like emergent hilarious behavior that comes from either really bad or really good programming. All right, here's an example of multi-agent pathfinding. And you may think that, well, multi-agent pathfinding is the same problem as single-agent pathfinding. We just make a bunch of paths, right? But that is not the case at all. When you get entities that are really close to each other, that interact with each other, it's very difficult to do multi-agent pathfinding. It's a much harder problem because things can get stuck on each other, etc. So this is kind of cherry-picking one of the worst examples of the original StarCraft, which had hilariously bad pathfinding in some cases. But down here is an example where we have a group of 10 tanks. And you're going to see that there's this little wall, and I'm going to try and move the tanks down here. You can't see my mouse. 1 second. I'm going to try and move these tanks around, like around this wall. And if you've ever played any RTS game before, if you're trying to get into an enemy base, there might be like actual defenders there. And you're trying to move this as a group so that, because if it wasn't as a group, they'll just be picked off one by one. And so the default pathfinding in the game, what it did was create a single path, and then all of the units in your unit group just sort of fight for position along this path. And so within seconds, you can see that, okay, this is probably not the way that we want to funnel into this base one by one, and maybe the enemy tanks just like, they kill us as we're walking into the base. So that's not ideal in terms of multi-agent pathfinding. Why aren't they all just moving as a group? Well, it's a difficult problem. Here's another case where I have told all of these SCVs over on the left to attack this larger structure. And you can see that it's kind of taking them a while. It actually does a decent job, but they do get stuck on each other in trying to attack this thing, right? So if the AI in the game was a bit smarter, it would be able to kill this structure faster. And so what players will do when they're confronted with this situation, if I can just back up, let me pause this, is that the players know that the pathfinding in the game is bad. So you might see a pro player like take these units and tell them to go here first, right? Because then they won't be getting stuck on these. Tell these to move here, tell these to move here, and then when they get them surrounding the building, then they'll finally give the attack command. And so you're kind of fighting with the pathfinding system as you're playing some real-time strategy games. But as time has gone on, pathfinding in games has gotten much better, and this is an example from StarCraft II, and I mean, this is 13 years old now, right? And it's much, much better. And so you get these cases of like flocking behavior in the Zerglings, and so StarCraft 1 used a tile-based A-star pathfinding system using a single path for all the units, and StarCraft 2 ended up using a triangulation-based navigation mesh for its pathfinding, which was able to find paths much faster, but it also did some things, if you can see here in this example, where as you group these Zerglings up, they're kind of able to walk on top of each other for a second, and then when they get to their final destination, they sort of spread out again. And so what they found was if you allow these little sort of cheaty behaviors, then the pathfinding becomes much, much easier to do, and it looks more fluid and stuff like this. So you don't get that case where, oh, I'm touching this unit by 1 pixel, so now let me move in a completely different direction, right? You can see that this looks much, much better, and actually looks like a swarm of insects trying to attack an opponent. Here's an example where we have, so this is from Dragon Age. I'm not sure which Dragon Age. And I kind of feel bad giving this example because a colleague of mine did the pathfinding for Dragon Age. But this doesn't have to do necessarily with the pathfinding, but sort of the realistic behavior with. And the thing is, coming to the goal in pathfinding and what you do to get to the goal and actually stop there can be an interesting problem when combined with other realistic geometries. And so the pathfinding here is fine until it gets very close to the goal.
My apologies. Can I help you?
Are you running short of healing herbs?
Yes. We've many injured from attacks by those cursed Templars. I need the herbs to treat people's wounds. It's too dangerous to go hunting through the hills to gather more.
And so like this sort of behavior in cutscenes is always kind of fun to poke fun at. But the pathfinding is pretty good in this game. This is just like this, again, a cherry-picked example where it kind of looks a little bit ridiculous. I kind of have to set up this. So this is from Fallout. I can't remember. Is this Fallout 4 or is it New Vegas?
I think it's 3.
3? Okay, Fallout 3. All right, so here you're going to see, as in a lot of Bethesda games, again, I hate to pick on Bethesda. I love their games. But as you walk into this area, an NPC notices you and comes up and is like, hey, I got a quest for you, right? But what the player does is it sees the NPC running toward it, and then it moves, and then the player moves like 2 steps to the right. and the NPC has to recalculate the path to the player. So here's the NPC coming. Okay, now it moved up to this like the top of this building. Yes, I'm going to wait for the whole thing.
Here.
Right? So, yeah, sometimes when you're doing pathfinding, you can get these like weird edge cases that make you look a little bit ridiculous. Now, in the next example, it shows why animation matters. Because you could have the most perfect, best paths imaginable, but then something in your animation system goes haywire, right? And then, like, this is what you're left with, and, you know, then this clip gets posted to Reddit, and I use it in my class. So, animation does matter when you're thinking about this sort of thing. So, pathfinding, most of you probably know what pathfinding is, and the reason it's important is because video game maps are often filled with obstacles, and those obstacles are collided into by NPCs, right? Like, we can't move through that wall necessarily, for example. Pathfinding is the method we use to determine which path an NPC should take from its current location to a goal location. And so, just like anything else, pathfinding is a decision-making problem, and you've got to go from somewhere to somewhere. So pathfinding attempts to minimize a cost of the path. That cost could be the total length of the path. So I want to take the shortest route somewhere. It could be something like fuel. So if you're like, there's a really famous story with UPS, I believe it is. It's either UPS or FedEx, someone who delivers packages a lot. And what they noticed, whoever noticed this was a genius, but the shortest path was not what they wanted in the end after they did like their GPS systems. So all the UPS trucks have a GPS system that's like administered by UPS. Now again, it's a delivery service, so I'm just going to say UPS. But what happened was, let's say you're at an intersection and your goal is to the left. You're waiting at that intersection idling for a very long time. And so what happened was, even though this was the shortest path, you could save fuel in some cases by taking 3 right turns instead of waiting at the intersection for like 5 minutes to turn left at these really busy intersections. And so they modified their pathfinding algorithm and ended up saving like 4% on their fuel costs, which is crazy if you think about it, how much money that must save a company like UPS just by modifying, okay, we're going to go with like the least amount of idling. So if I don't have the left turn right away, take this other path, and it ended up saving a bunch of money. You could think of another thing where you have some sort of, I don't know, tower defense type game where you may want to minimize the damage taken, right? So, okay, the enemies have a bunch of towers. Maybe my NPC wants to go around those towers rather than taking the shortest path through them, or any other arbitrary function, right? So your pathfinding algorithm is going to be some optimizing problem that takes in a cost and attempts to minimize that cost. So if your boss at the game company says, make a pathfinding system for us, well, there's a bunch of considerations before you just start programming your A-star algorithm, right? That may not just be the solution in all cases. First of all, is your problem single agent or multi-agent, right? So we saw that in that case with the tanks, if there was just one tank, then that solution was fine, right? It made a great path, but as soon as it got to a multi-agent problem, it was no longer fine. You may have to calculate one path for each thing, or some other method. Is it single goal or multi-goal? So for example, if you're making an action RPG like Diablo, you may have a bunch of NPCs trying to get to the player, right? So 100 zombies are trying to attack the player. In another case, you may have an NPC that has to, I don't know, ring an alarm or something. So maybe there's 3 or 4 different alarm buttons in the level, and they just have to get to the closest one, right? So, okay, now I have to pathfind to the closest of many possible goals rather than just to a single goal. Is it a static pathfinding problem, or is it a dynamic pathfinding problem? So, for example, if it was static, if nothing ever changed in the environment and there was nothing moving around for the enemy to collide into, maybe we could just pre-compute all the paths and store them in some file. Or maybe there's a bunch of things moving around, and so we'll have to do dynamic pathfinding in our game. We have to consider the space representation of our environment. So how are we representing the game, right? So for example, if you're looking at assignment 2, where we had this geometry wars, imagine that we're trying to do pathfinding for one of the enemies, right? Well, that's a really open system. Like, you can move in any direction. There's no walls to like block you, so it's really open. So you don't necessarily need a representation in that case if I can always move from point A to point B in a straight line. Sometimes we have a grid representation. You probably have PTSD from doing grids in 3200 if you took that class. So in a grid system, you're chopping up the game into squares or rectangles, and then your algorithm is operating on those squares or rectangles. You may have an arbitrary graph representation of your problem. I think I have slides on this, so let me just see something. Oh, okay, so I actually have slides explaining all this that I forgot about, and I looked at this right before I came. So also you have, I'm going to skip that because we have a slide about it, and then you also have considerations about movement directions. So for example, maybe you can only move up, down, left, or right. You could move at arbitrary angles, move between graphs on a node, etc. So now that I remember I have slides, let's move on to those slides. So the pathfinding considerations, here's an example where I have a single agent and a single goal. So, okay, just compute a path from here to here. Here's an example of multi-agent single goal. And the case where this happens the most is in games where you have a bunch of NPCs that are just trying to get toward the player, for example. You could have single agent multi-goal, which is kind of the opposite problem, where maybe you have to go to each of a series of locations, or you have to choose from the closest location or something like that. The space or action representation is a super important problem, and the ideas are linked. So the space representation that you choose is intrinsically linked to the actions that you're allowed to perform in your pathfinding problem. And which representation to choose is based on a bunch of factors from the game's design. And so the choice of space representation in the pathfinding engine will determine which movements can be performed. So for example, if you have sort of no representation and you're allowed to move in any direction at any time, then you could have this path, this is nice flowing path, and this is like an example of arbitrary movement in your game. Okay, so you can move in any direction, there's nothing stopping you. In another case, you may have, okay, I'm only allowed to move in straight lines. So many older games had systems like this. Okay, I'm going to walk in a straight line, then I'm going to turn, then I'm going to walk in a straight line. And so a shortest path in that system may look something like this. You may have a game which is on a grid, right? And so in this grid, you have 4-directional movement, or maybe you have 8-directional movement, etc. So that's one way of looking at it. And another case, you may have predefined nodes of a graph that you're allowed to walk between. So here, for example, maybe the player can just walk between, or the NPCs can walk between all of these yellow circles that I've drawn, and then you're just doing pathfinding based on that graph. In another case, this is how I believe StarCraft 2 ended up working, but it used triangles instead of arbitrary polygons. But here we have what's called convex polygon movement. And the cool thing about convex polygons is that by definition, a convex polygon means that you can see any point in the polygon from any other point within the polygon. So what that means is if you are an NPC or a player inside one of these polygons, you know that the shortest path between that point and any other point within the same polygon is a straight line. And you know that there'll never be an obstacle in that straight line because it's within the same polygon. And so what happens is this is sort of a two-layered pathfinding system, where first, if I'm in this polygon up here and I want to get down here, then first I would do the pathfinding at a polygon level, because I have mapped, okay, I can move from this polygon right here to this polygon, or I can move to this one, or I can move to this one. And so there's sort of a graph of polygon movement. So I'm going to figure out from which polygon to which polygon I want to move. And then at the very end, when I get to my destination polygon, then I know, okay, I can just move in a straight line toward that final goal. So what happens is, depending on the movement system and mechanics of your game, you're going to choose one of these representations for the pathfinding system. And then within this system, that is how the actions are going to be searched over or optimized within your pathfinding engine. So choosing this state representation matters, right? It matters a lot. So the memory size is dependent on the representation. So for example here, if this, a grid-based system, may be really easy to do the pathfinding in, but storing all those grid locations may take up a bunch of memory. Versus this graph-based representation, maybe you don't have such fine-grained movement in the graph-based representation, but you only have to store a few dozen nodes, right? So the memory is definitely affected by your representation choice. Also, it defines which actions are possible. It defines which algorithms are applicable. And so you're going to try and somehow find a balance between the computation required to find a path versus the final path's accuracy. So typically what happens is our game is going to have some movement in the actual game, right? Then, instead of trying to do the pathfinding in the game at the level of movement of the actual game engine, because that's typically much harder, right? How would I do pathfinding if I can take like arbitrarily curved paths in our game? So typically what we do is when we go to make a pathfinding engine, we choose some sparse state representation for easier computation, and then later, once we've done the path in that representation, then we refine the path to look more realistic. And I'll give you an example of this in a few slides, because I know that's like, what does that mean exactly? I'll show you an example of that. However, an industry standard has sort of emerged over the years, which is called a navigation mesh. And what if my game has a sort of arbitrary geometry, right? So it's a 3D game. I've got all these surfaces. I can't necessarily make a graph or a grid. So what happens then? So there is a graph structure. We're going to make a graph structure within our environment to enable pathfinding. And typically, this graph is composed of polygons, and it's called a navigation mesh. And I'll have an example in a second. So most game engines now, if you download Unity or Unreal or whatever, they're going to come with the software to build and edit a level's navigation mesh. So you can basically paint a navigation mesh onto your environment and define which areas are walkable and which areas are not, and then the game engine's pathfinding will just handle it for you. And so we're going to talk about navigation mesh much later, well, on the next slide, so I don't know why I had that one in there. Let me just eliminate that right now before I just delete that. All right. So we're not going to talk about that much later. We're going to talk about it right now. So here's an example, I believe, from an earlier version of Unity. And what we see here is that we have some 3D level geometry. And we want our NPCs and our player to be able to navigate through this somehow, right? So what we have to do at some point is say, okay, certain areas of this environment are walkable, and certain areas are not walkable. And in this particular example, this 3D environment has this sort of wall in the middle here. So I've got an environment over here where I want the user to be able to pathfind, or the NPCs to be able to walk. And then I have another area over here where I want them to be able to walk, but I don't want them to be able to walk on top of these towers, but I do want them to maybe be able to hop over this section of the hedge, but maybe not this section of the hedge. And so what I do in order to enable this is I draw a navigation mesh on the parts of the level where I want them to be able to navigate, And then if it's an NPC, the pathfinding engine will take care of it. If it's the player, then it'll say, okay, these are the areas where the player is legally allowed to traverse. These can be extended in like 3 dimensions. So for example here, maybe you have like a Spider-Man game and you want the user to be able to walk on these blue areas of the map. And so, okay, they can walk here, and then they can actually walk on this vertical wall as well. And then I've defined some sort of transition here which says you can, if you walk over here, then you're allowed to start walking over here on the blue. And what this may look like in its final form is something like this. So if I have a game where, let's say, I'm not allowed to jump in this game. Like earlier video games, you're not allowed to jump. So if anyone's played Ocarina of Time for the Super Nintendo, like one of the first 3D Zelda games, you couldn't actually jump. But you could hop between parts of a level, right? If there was like a little gap, you could jump over it, but there was no jump button. It would just jump for you. So how are they able to do something like that? Well, I'm sure Zelda wasn't written in Unity, right? But what you could do is make a navigation mesh which has these, so you can walk on the blue parts here. You've defined, okay, I can walk up these stairs. And also, you can define these little nodes here that say, if I walk onto this one, then the game will push me over here to this thing. And so these navigation meshes are very powerful, but you end up spending a lot of time in your game like marking up the game. So there's a lot of markup here to say what this pathfinding engine can do. So as this technology becomes more mature, and it's been around for 20 plus years at this point, some game engines you can just hit a button and it'll make the navigation mesh for you, and then you can go in and you can edit it to say, no, I don't want them to be able to walk over here. I don't want them to be able to walk over here. So we're not going to be making an arbitrary navigation mesh in our game engine. Don't worry. That's not why I'm going through this. I'm just showing you okay, this is what more modern games will be doing. So single agent pathfinding, once you've chosen a representation, many graph search algorithms exist for finding shortest paths, each with their own properties, such as memory requirements and time, running time complexity, etc. So some common algorithms, maybe you could just get away with doing a depth-first search if you have a simple environment, or Dijkstra's algorithm, or A*, etc. These heuristic search algorithms have been around forever, and I'm sure you can just Google them if you want to. And most video game pathfinding has traditionally used some variant of the A* search algorithm. So just very briefly, without going into it too much, the A* search algorithm is by far the best, the most well-known best first search algorithm. And so what happens is you evaluate nodes based on this f of n. So down here, this f of n, which is equal to g of n plus h of n. What are those? G of n is essentially the path cost so far to a node that you've searched to, and then h of n is like a guess at how far you have left to go. And so what happens in the A* search algorithm is let's say I wanted to move from here to there. Then, okay, maybe I'm currently here in my pathfinding. I see how far I've come. I have a guess at what direction I want to go in, and the combination of those two things sort of determines the direction in which I search exhaustively through this environment. And then eventually I've searched exhaustively through everything and I've found the best path. So here's the A* search algorithm. I'm not going to go into the details of this, but it's there in case, hey, maybe you actually did want to implement A* in your game. And if you do, I highly recommend watching the lectures from 3200, which are publicly available on that topic. So I'm not going to take up a bunch of time in this class with that. I'm not even going to mention what an admissible heuristic is. Let's just pretend that that doesn't exist. That's all there. If you want to do A*, it's all there in my 3200 lectures. But I do want to give this because maybe some people didn't take that course, and I just want to give a little bit of a demo, which is this. So we do have some sort of pathfinding environment here. So this is our video game map, and if you're doing a top-down 2D map, you can absolutely use A* for doing your pathfinding in your game. So for example, if we're looking at a StarCraft level, how do I get from here to here? Well, this is the shortest path going from here to here. And what this little demo here is for is you can play around with all the parameters. Like, okay, here's a weighted A star. Oh, look, this finds a path in many fewer nodes, but in weighted A star, you trade optimality for performance. Maybe I could look, okay, this is breadth first search. Oh, wow, that's like really bad. I don't want to use breadth first search. Uniform cost search, okay, maybe I don't have a good heuristic, so uniform cost search is equal to Dijkstra, all sorts of crazy stuff with pathfinding. But this is just a little demo that I wrote that you can play around with if you want for pathfinding. But again, pathfinding is such a huge part of the other courses that I teach that I don't want to bog down this course too much with those materials. So that demo is there in the slides if you do want to play with it. However, I am really interested in showing you what happens in the actual pathfinding workflow of like a modern game if you are going to make one of those. So, first, identify the problem that you're solving. This may seem really intuitive when it's written on a screen in front of you. You're like, of course. But you'd be surprised how many people just jump into coding without truly identifying the problem that they're working on. And then realizing halfway through that there are all these constraints that they forgot about, or a time limit, or memory limit, or whatever, that they didn't really take long enough to think about in the first place, and now they have to recode everything. So truly spend a bit of time identifying the problem that you're solving. Is it single agent? Is it multi-goal? Is it whatever? Then, construct a space representation that is going to conform to the constraints of your game engine or the platform that you're running on. You're going to probably choose a different pathfinding algorithm if you're running on like a PlayStation 5 versus a PlayStation 1, right? Not that you're making PS1 games, but you get what I'm trying to say. Then, decide which actions are possible in this space representation. You are given a start and a goal location. Typically, this will come from the game design documentation. So, for example, it'll say, when this type of NPC sees the player, they're going to run straight at them. Or maybe this type of NPC will run away from the player because they're afraid of them, etc. Then you're going to apply an algorithm which finds a path. Then you are going to follow the path from the start to a goal. So let's look at an illustrated example of this. Let's say that this is our environment. Okay? So first, let's identify the problem that we're trying to solve. So first, we have this is like a 3D-ish environment. You could actually probably represent this by 2D because nothing overlaps, but it's a 3D-ish environment. So what's the problem we're trying to solve? Okay, in this example, let's say that we're just doing single agent, single goal. So maybe my agent is going to be somewhere in this environment, right? Could be anywhere in this environment. And then the goal could be anywhere in that environment. So we've got to define the parameters of the problem that we're trying to solve. Next, we are going to choose a space representation for the game. So something that sort of makes sense to make the pathfinding a little bit easier. Okay, so let's take these regions. So we're going to chop up our game into regions or polygons or a grid or something that's a little bit easier to work with. Then we're going to be given a start and a goal by something. Maybe the player has right-clicked or the NPC is trying to run, etc. So this is the start and the goal. And what we're saying here is that, okay, I've identified that the player is in this part of my space representation, and the player needs to get to this other part of the space representation. And so we are going to take this, and maybe now we said, okay, what actions are possible in this state space? Well, something that might be intuitive is, okay, we've sort of formed this graph of polygons here, so maybe the actions that I can take in my pathfinding engine are to move from one polygon to any adjacent connected polygon. We run our pathfinding engine, we get something like this, right? So this is the path that we've found through our space representation. And then what we have to do is once we have that, we have to translate that into an actual path that can be taken by the NPC or the player in the game, and then we do the path following part where the NPC is actually guided through the level somehow to follow the path that, that we've given it. And so if you did do 3200, then you're very familiar with everything kind of up to the last part, which is the actual path following. So let's have a look at path following, because it's just as important, in my opinion. So now that we have a path, how do we make our agent traverse it in the game? So one of the simplest possible ways is waypoints. So each point along the path is a waypoint. So for example, if we have our 2D grid, then maybe just every grid cell is a waypoint, and we're going to say walk from one cell to the next cell, then to the next cell, to the next cell. So the path to the next waypoint is always clear. So we've chosen our waypoints somehow so that we know we can always walk from one waypoint to the next. And then we stop when our NPC reaches the goal. And typically that is when they've reached the final waypoint. So for example, in this example of this 2D grid, maybe I only have, so I've chosen, so it's possible that in my actual game, I can move in arbitrary directions, right? But for my pathfinding state representation, I've chosen a grid, and I've chosen 4 directional movements in that grid, right? So your pathfinding choice of state representation and actions could be very different from what you're actually doing in the game. So once we've found our optimal path here, I've just said, okay, every cell is a waypoint. Now, you could say, okay, I'm going to go from the start to one waypoint, to the next waypoint, to the next waypoint, to the next waypoint, to the next waypoint. And what can happen here is if your waypoints are too close together, you're going to get this jerky motion in your game, right? Where, let's say that your character has some acceleration in the game. So now, okay, follow the waypoints. Well, I accelerate, maybe I only get up to like half speed, and then I reach this waypoint. And then I kind of stop. Then I go, okay, accelerate again. So the pathfinding is like, you know, it's really jerky motion. It's not really good. So what could we do? Well, we could do something where we're going to say, hey, these would also be fine as waypoints, right? So I can go between all these waypoints, and this increases the distance between waypoints, so now maybe the movement is a little bit more fluid. But maybe now you realize, okay, well, our game isn't constrained by 4-dimensional movement, or 4-directional movement. So maybe what I could do is take these waypoints and then do something where I say, well, if I can move in any direction in my actual game, then let's take the furthest waypoints where I can still see the waypoint. So what do I mean by that? Well, let's start at the start. Do I have a line of sight between this waypoint, or the start, and this waypoint? Yes. This one? Yes. This one? Yes. Yes, 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 yes. Maybe no here. So what I'm going to do is I'm going to say, hey, this is the furthest waypoint which I can actually see from the start, so why don't I just make that the first waypoint? Right? So I can just move directly toward that waypoint. So now I've completely eliminated this like really jerky movement where I'm like walking like a robot and then turning and then moving like this, and I've got something better. Now what I could do is say, okay, that's a much better path, but I'm still doing this where I walk and then turn and then go in another direction. So what we could do is refine this path even more so that I get a bit of a smoother movement, a more realistic movement. And the way that I can do something like that, one of the ways to do that is called steering, and that will be introduced at the end of this lecture. And your assignment is going to have some sort of steering in it, okay, as a pathfinding measure. Or a path following measure, excuse me. So while we still have a bit of time, I'm going to talk about other pathfinding methods that were not in 3200 and why we would use those and what they're for. One of them is called a vector field. And so these are also called flow fields or influence maps or vector maps. And what it is a very efficient structure for pathfinding in the case of many paths to a single goal. So any case where we'd have a bunch of NPCs that need to go to a single location, consider using this type of pathfinding. and we must balance the computation time with how many NPCs, etc. So in games where we have, let's say like Diablo or Path of Exile, it's a really good example to use for this type of problem. We're going to have possibly hundreds, if not thousands of entities trying to pathfind from their location toward the player, right? Just a bunch of zombies running toward the player. And you might say, okay, how would I do that? Well, it might come to mind, well, I know how to get a single NPC toward the player. I'll just run A star. But if you have 100 things, are you going to run A star 100 times and have 100 different paths that everyone is trying to walk on top of each other? It's not a great solution. So this example here, we have, I think, what is that up in the top left? Particles, 20,000. So there are 20,000 particles trying to get toward the player's mouse, right? So you can think of this as a game like Diablo or Path of Exile, where we either have particles or NPCs trying to pathfind toward a level, toward a player in a level. And there's 20,000 of them here. So we're probably not doing 20,000 A star calls every frame of the game. So what is happening? How are we doing this pathfinding? It's actually remarkably simple. And it's one of my favorite examples. And when I did 3200, I had an actual assignment on this where you would make literally this assignment. And I think my solution code was doing like 500,000 particles, like at 60 FPS. Like really, really cool, simple algorithm. So what do? First of all, we're going to break up our space representation into a grid. So we have a grid system that we overlay on top of our environment. Each of those grid cells is going to be a representation of like that part of the space of the environment. And so what we have here is this idea called a distance map. So this distance map, let's say that the player is right here. Okay, so that this is the player. What we do is we do a breadth first search in 4 directions outward from the player. But what we do is every time we go to a new depth of the breadth first search, we increase the number. So we're going to make a new grid structure where we're going to store a bunch of numbers. And what we have is, at the end, a grid which stores how far there is to travel between this grid cell and this destination. So if this is the player, and there are a bunch of NPCs scattered around the level, what you have, after you've computed this distance map, that I call it, and maybe no one else in the world calls it that, is you have a very easy, efficient way for that NPC to look up how far they have remaining to travel to get to the player, right? So you can see if my NPC is right here, well, I'm going to just do the math to say divide my X position by the grid spacing, divide my Y position by the grid spacing, so I know I'm at that grid, and I know that that NPC has 7 distance, approximately, to get to the player. Now, BFS is not an optimal pathfinding method, but for this, it's good enough. Then, what we do is really, really simple. We take those numbers, and in order to get from where I am to that single location that I want to go to, all I have to do is go in the direction of the lowest number. Because if I go from 7 to 6, I'm closer to my destination. So here what we've done is we've taken that grid, and at each grid location, I'm storing a vector. So it's just an X and a Y pointing in a specific direction. And so for example here, you can see this 7 is pointing down toward this 6. The 6 is pointing toward the 5 is pointing toward the 4 is pointing toward the 3. And so at any point, if I want to know where to go to pathfind toward the player, I just follow that vector. That's it. And so I have 100,000 NPCs in the game, and they all know exactly where they have to go, based on one breadth first search, essentially. So it's super powerful, and I assume that this sort of thing is how these games are doing their pathfinding. I can't think of anything else that would be remotely as fast. So if you take that previous example and you look at the distance map, this is what's happening, right? So as the mouse is being moved around, this distance map is being calculated, and then this vector field is being calculated. And really, the NPCs don't even know or care that they have a particular goal in mind, because they're just following the vector field. That's it. They're just going in the direction that the grid cell that they're standing on top of tells them to go. So it's such a cool, simple algorithm, and that would be like kind of easy to implement for your non-trivial pathfinding in your game if that's what you want to end up doing. Okay, so the last 4 slides, those videos came from this article, so I just like to cite things whenever I can. And if you're interested in implementing vector fields, then there's some pseudocode and stuff on this article, but I won't go into it. Taking vector fields to the next logical step, we get to this thing called influence maps. So influence maps typically incorporate other logic into your pathfinding than just simple distance to goal, right? Because that vector field example was just, hey, how do I get there the fastest? And influence maps are sometimes used when it's very difficult to come up with an objective function for other algorithms, right? So for example, maybe we want to go to the player in the fastest way possible, but we also kind of want to avoid taking damage. How would you put that into the A* heuristic function or into the goal function, right? It's kind of difficult. So here's the idea behind influence maps. Now, in practice, it doesn't always work out to be this simple. There are a few other things that you have to do, but this is the idea behind influence maps. So let's say the very simplest possible form of influence map is I've got a start, I've got a goal, and maybe there's one grid cell of my environment that I want to completely avoid, right? So there's an enemy here, and I want to completely avoid it. So my influence map, which this is, it's a very simple form of influence map, just says avoid that enemy, okay? So what we've done is just say that enemy is off limits, I can no longer move there. So that's the very trivial, uninteresting way of looking at influence maps. So what we do is we say, okay, I'm going to do the same vector field pathfinding, but what I'm going to do is just, there's no number here. We just call it infinity or something like that. So we'll never walk on this grid tile. Here's another example. Maybe this is an actual game where you're moving through the water in a boat, and if you get close to the shore of this island, then you have a chance to be damaged or something like that, right? So you want to be going from the start to the goal as fast as possible, but you want to avoid the shore if a path exists where you don't have to go through it, but you don't want to just say it's illegal to go on the shore. So what you can do here is apply some influence to that area. In this case, this is a negative influence. But what this 10 value means, essentially, is that I would rather go 10 more distance in another direction than step on this tile. So what we do is we do the same thing that we did before, but we just have these increased values of 10 on those particular locations. And so what you can see here is that as this player, well, we're going to move in the least direction, right? So I go from here to the 16, to the 15, to the 14, to the 13, and you can see how it's avoiding this area of the shore because we've basically said, I don't want to go next to the shore, but if there was no other path, we would still take that direction. But now you can see why the simple math doesn't just work here. We've got to have something a little bit extra because let's say up here was blocked off and down here was blocked off, right? Then if I was here, I wouldn't be going from 10 to 19, right? That's not actually our algorithm of just going to the least thing. It would just kind of be bouncing off the shore here and not actually going on it. So this is the idea of an influence map, avoiding this type of behavior, but there's a couple of extra steps to it. Let's say now that we have this enemy down here, and we don't want to go, maybe this is like a turret, and we really don't want to go in the area around this turret, so we give this these values of 50, and then, okay, right here, this is the shore and a turret, so this is a value of 60, so you can see what I'm talking about here. You give these regions some sort of influence, either I want to go here because this is like a health pack, or I don't want to go here because it's near an enemy. So that's the idea of vector fields and influence maps and how they can be used. Now, how did that smooth movement happen? You saw the smoothing of that path that we had. We also saw those particles were kind of taking these cool turns rather than just being really jerky movement. How can we implement something like that, especially on the project, because that's a requirement? Well, you can accomplish this with a steering behavior. And a steering behavior is essentially, you can see it as like a framework for controlling autonomous agents, such as robots. I think that like in the Battle for Helm's Deep CGI for Lord of the Rings, they used some flocking behaviors and steering behaviors, which is pretty cool, and also NPCs in games. So what steering does is it adds more realism and fluidity to agent movement, and it can enhance the experience. So basically, what steering does is it turns an NPC into a car, right? So before, where we were walking like this, and then turning, and then walking like this, now we are steering with a steering wheel, right? So in order to turn, I've got to be like, okay, I'm going to steer, and I'll go in like a smoother path. The math turns out to be really simple, so it's not like a huge physics problem. We're just adding a smoothness to the direction of our movement. Steering can be kind of fun to implement. Oh, excuse me, that's probably super loud on the mic. So steering can be really fun to implement. There's a bunch of parameters in steering, or there can be a bunch of parameters. We're just going to talk about a couple and see which effects are produced. So, at its core, steering smooths the movement of entities in games. It can also be used to like chase enemies. It can also be used to avoid enemies. And it can also be used as like a rudimentary form of pathfinding, if nothing else works. But what we're going to be talking about is the smoothing of movement using steering. So of course, changing directions instantly, stopping on a dime, all of these things look really bad in our game. And so steering acts as a force that smoothly guides an entity toward a target. And it will be part of the project. So what I mean by that is, if my eventual goal is over there, and I'm currently heading in this direction, steering is going to act like a force and like gradually push me in that direction. And that gradual pushing in a direction, picture some, like if you're trying to walk in a straight line and someone is literally just nudging you in that direction, right? And you're slowly turning, that is what the steering force is doing. So here's an example of the math of steering. So I've got an entity, and that entity is going to have a velocity at some point in time, right? So that velocity is this arrow here. So that entity is going to be here on the next frame of the game. So that's what's happening. I've got an entity that's moving, and that entity is going to have some sort of target. So say your game is, I want to collect food pellets, or like Nibbler, or one of these old school games where you're just moving around collecting food. All of a sudden, a food pellet spawns. All of a sudden, a health pack spawns, whatever you want to go towards. And of course, I'm giving this a contrived example because of the slide where I was just randomly going somewhere and then on the next frame something spawned. But this could have been a behavior that's going over time, right? It doesn't need to have just spawned, for example. Basically, I'm heading in some direction, but I want to be going in this other direction. And so what we would do if we were just new programmers is we would say, okay, I'm going to take my current velocity, and then on the next frame, I'm going to have that desired velocity, right? And so I was going in this direction, then instantaneously, I'm going to turn in this different direction. So because the desired distance is probably greater, that like it's bigger than my velocity, what I would do is I would take my velocity, I would figure out that length, that's my speed, then I would form a new vector that's pointing toward the target, and I would normalize it and then multiply it by the speed. So that's what I would get, that's how I would get this desired velocity. And so what we do here, we already know this, but we would take the desired vector. We're going to do several calculations to that. We're going to take the target's position, subtract my position. That is the dashed red vector, so that is this big long vector. Then I'm going to normalize that vector so that it has length 1. And then I'm going to take the desired vector and multiply it by my current velocity's length. So my current velocity's length is my current speed, And so I've changed essentially my current velocity with this speed into this velocity with this speed. But this is the bad thing. This is just the instantaneous turning, and we want to change that. But this is what I have right now. What I want to do is, instead of going from here to here instantaneously, I want to slowly, over time, move. And you may think this involves some sort of crazy curve or something like that, or some parameters or some x squareds or something really fancy, but it's not. It's just a force steering us toward that vector. And so if we take our current velocity and we steer all the way instantaneously, all the way to this desired, then that's what we were doing before, essentially, right? So this steering vector is the change between my current velocity and my desired velocity. And so that's the green right here. So if we take desired minus velocity, that is the change between this point, and so that's that green one. And if we just take desired minus velocity, and we add it to velocity, what we get is desired, and so that will be the instantaneous change. So what we can do is, we scale the steering vector. And what this is called is the steering force. So we take the steering vector and we multiply it by some value between 0 and 1. If the scale of the steering vector is 0, then we will just keep on with the same velocity, right? Because we're just adding 0 to our velocity. If the force, the scale is 1, then we get to this red one, and that's what we want to avoid. And so what we want to do is choose some pleasing value through experimentation or whatever. Typically, it's like 0.1 is decent, so steer 10% or steer 1% every frame toward your target. And what we'll get is that we've scaled this steering force, and so now on the next frame, instead of heading in this direction, we'll actually be heading in this direction. Okay? Now, this vector here, if you take this vector and you actually swing it down, it'll look more like this, right? It'll go around, but I've just drawn this pointing to this steering vector because that was easier to draw. So we scale the steering force, we add it to our velocity, and what we get is movement toward that desired velocity, but not all the way to the desired velocity. So how do we calculate this actual vector? So actual here means the actual direction I'll be moving on the next frame. Well, we're going to choose some scale between 0 and 1, making sure not to choose 0 or not to choose 1. Then we calculate the green dashed steering vector. That's just desired minus velocity. Then we have our scale, and we multiply that by the steering force, and then we just add that to our initial velocity. It's super simple, right? Like, you could all do this right now in your assignment. It's no problem. So if you want this in terms of like actual pseudocode, now I've put the entire diagram up here on the slides, so you can have this in the slides, but of course in the video my face is going to be on top of this, so I apologize for that. But given that I have a current velocity, a current target, and a current scale, here's the code. My desired is target minus position. That's the dashed red line. Then I'm going to take that and divide it by the length of my current velocity, so that I want to go in that direction at the same speed that I'm going right now. So I multiply it by the length of my current velocity. Then I form the dashed green line by taking desired minus velocity. I multiply it by my steering scale, and then I add that to my velocity. Okay? So that's it. That's the math of steering. However, there are types of steering. So I have a current velocity and I have a target. What we just talked about is a seeking behavior. I am going to seek out that target, meaning I'm just going to be chasing it around in my little car, right? Instead of seeking, let's say I want to get to my target. Is this actually the best behavior, right? This is fine if my target is stationary, but if my target is also moving, then this is not the best way to do it. The best way to do it would be this thing that's called a pursue behavior. So in a pursuing steering behavior, instead of taking my desired velocity as the target's position, my desired velocity will be where I think the target will be at some point in the future. Okay, so I take the target, add its velocity, and then do the steering calculation, and that's called a pursuing behavior. But let's say I've casted a fear spell, or I'm a super high level, and there's an NPC that's actually afraid of me. Well then, if I want a fleeing behavior using steering, all I would have to do is take that desired velocity that we talked about and multiply it by -1 to make it go in the opposite direction. So now, instead of, like, if I'm going here and there's, like, I don't know, if I'm a robber and a cop spawns, then instead of going towards it, I'll be slowly moving away from it until I'm going 180 degrees in the opposite direction. Now, that's all well and good, but there's a problem with this, and that is what happens when we arrive close to our destination. So one issue is with steering is that when we get really close to the target, we start to oscillate. And why is that? It's because if this is our target over here, for example, when we arrive near our target, we're going to go probably overshoot the target a little bit, right? Because we've gotten a certain velocity. And then, oh, look, now I've got to steer around, and I got to go through it again. And I steer around, and I go through it again. And I steer around, and I go through it again. And it would be really weird if you just, like, instantaneously stopped here. And so there is something that you have to choose on, which is called the arrival behavior. And so this arrival behavior is very important. And the simplest solution to this is just to scale the speed somehow as it approaches the target within some distance. So you've got your speed, you're going at that speed the whole time. Picture you're parking in a parking lot. So you're driving 50 down Prince Philip, right? And then you see your parking spot. You don't just, like, instantly pull the handbrake and, like, slam into your parking spot, right? You slowly slow down so that you make this sort of accurate stop at your final destination. So that's one way of doing it. There's no best algorithm for this. The arrival behavior is just something that you have to experiment with. So, for example, if in your game, the canonical example that people typically use for steering in their game is some sort of heat-seeking missile, right? I have a heat-seeking missile. Instead of it just, like, turning and moving toward the player, it slowly turns toward the player, and you make it, like, an interesting speed so that the player could avoid it, and so the player's a little bit faster, and now they jump over it, and then the rocket comes back, and, like, it can make for some interesting gameplay. So in that case, maybe you don't have an arrival behavior for a heat-seeking missile, right? Like, who cares? But if you do have a car or something like that, then you would need arrival behavior. So here is the seeking behavior as an example with this cute little kitty. And I didn't program this is someone else's. But you can see here when I choose a new target location, it slowly steers toward that target and just looks a little nicer, you know? And these little things are really what make the game. If you played a game with this in it versus a game where it just, like, instantly turned toward the target, you'd feel that, like, something was off. Maybe you couldn't explain it right away, but now that you've seen this, you can never unsee it, and you'll see it in every single game that you ever play. Like, how do things change direction? Something you've probably never even thought about, but is such a huge deal, like, for the look and feel of a game. There's also things called avoidance steering. So here we have a hockey game, and I see, okay, I want to get to a particular location. I have a current velocity, but I want to avoid these two other hockey players because they're going to crush me, right? So I can avoid the closest hockey player so that my steering behavior is used as an obstacle avoidance technique. And so this starts to get into the realm of, like, path finding a little bit, but you can do it through path following. So you could have a hockey game where all of your pathfinding is done with steering behaviors, and that would be pretty cool. Oh, you can also do a sports game for your project if you want. I don't know how into sports games you are. And steering can also be used in multi-agent pathfinding situations where, like, okay, we've got a little traffic jam here, but you can see that I'm trying to at least steer away from these things. And as you steer away from things, you avoid them, and the pathfinding is a little nicer, right? So if you're thinking about multi-agent pathfinding, like, okay, in a game, you've got maybe a single algorithm controlling everything. But humans in the real world, animals in the real world, they do not have a centralized pathfinding algorithm. calculating the path for everybody and then saying, Dave, you need to go in this direction, and Joe, you need to go in this direction. No. We have our own little rules, right? And so there's another thing called flocking, which I'm not going to get into in this class because we're almost out of time. And I've timed this lecture surprisingly well. But a flocking behavior is something where it's like, okay, how do birds fly? You see the flock of birds, like they're doing something crazy, coordinated, right? Turns out you can reduce that really complex looking behavior to something like keep a distance of about 1 meter of the bird in front of me and position it so that I'm halfway between the two birds in front of me. And then the only person making any decisions in the flock of birds is the lead bird. It's flying around, and everyone else is just like, oh crap, I got to readjust myself with respect to the birds in front of me, right? So if you're walking down a busy street in New York or something like that, you're pretty much doing the same thing. I'm going to keep a little bit of distance so the crazy person in front of me doesn't like stab me. I'm going to walk behind them, and if everyone starts moving to the left, there's probably some obstacle up there, right? There's some construction or something, so I'm just going to follow this crowd to the left, and then I'm going to do a little bit of steering behavior so that if someone is not using the same algorithm as everyone else, I can avoid them. But it's just these little individual rules that when applied in some sort of consistent manner make this really complex looking behavior. And so stuff like this, there's an entire branch of robotics called swarm robotics, where the idea of swarm robotics is that you get complex looking behaviors from simple rules being applied to a bunch of robots. That's out of the scope of this course, but just in case you are interested. And there's this thing called OpenSteer, and there's a whole demo there, but it's going to be cut off of the video, and you can go look at this if you want more ideas for steering.